Welcome to the continuing discussion about exponential functions and equations. And in this video, we're going to talk about techniques of solving exponential equations by using logarithms. If you missed the last video where we talked about solving exponential equations using log bases, then you can go back to that. Remember that we talked about when exponential equations are not able to be written so both sides are exponential expressions with the same base, that we needed to use logarithms to solve those equations. And we're going to walk through this example of solving this exponential equation where we can definitely say that we don't know a power of 70 that will get us to 84 or vice versa. So the quickest way to actually solve this equation is to kind of undo what's being done, right? 84 is the base of an exponent, and that's where you find that x. So we can totally undo that by taking the log base 84 of that left-hand side. So if we take a log with the same base as the exponent on both sides, which we'd have to do, right? Then we actually eliminate everything on that left-hand side, right? Everything here except for x. And so my left-hand side becomes x, and then you can leave it like this, or you can write it as a ratio of two logs, which is using change of base property. Which would be the log of 70 divided by the log of 84. Now, it really depends on what your professor or teacher wants you to do here. So when I am interested in an exact solution, I am good with this form or this form, but different people have different kind of philosophies on that. I definitely like you to be able to get to this form because some of you don't have calculators that can actually evaluate this. And so that would be the next step. If I'm looking for an approximation, I'm going to put this into my calculator. And some of you do have calculators that will do this. But either one, we're going to put in our calculator and we should get an approximation of about 0.959. Now, there's strengths to both of these answers, right? Because this is an exact solution, but not very many of us know what number that's about, right? We don't know that is approximately 1. We just don't know that. But we do know that when we approximate it, we can kind of relate to it better because we do know that 0.959 is just shy of 1. Right? And that also allows us to pretty easily just sub that back in to our equation and check our work. Now, when you do that, you probably won't get exactly 70 out because this is an approximation. You'll probably get something really darn close to 70, but not exactly 70. So I kind of alluded to the idea that there's more than one way to do this. And so I'm going to show you another way to solve the same equation. So another way we can do this is to take a natural log of both sides of this equation. All right, and so then we would have ln of 84 raised to the x is equal to ln of 70. And we would do this because then I can use the power rule and take this x and treat it like a coefficient. Okay, and so that would look like this. X times ln of 84 is equal to ln of 70. And then we could use what we know about isolating x. X is multiplied by ln of 84, so to isolate x, we would divide both sides by ln of 84. And notice they look an awful lot alike. Ln of 70 divided by ln of 84 and log of 70 divided by log of 84, they're the same thing. They're just a different base of that logarithm. And you can sub that into your calculator and verify that, but definitely you should get the same answer. All right, next example. E to the t is equal to 1,000. All right, so we're going to go ahead and take a log with the same base as the exponent on both sides. So the base of this exponent is e, so we're going to take a log base e of both sides of this equation. Log base e of e to the t is equal to log base e of 1,000. But wait a second. Isn't log base e the same thing as ln? It certainly is. Ln of e to the t is equal to ln of 1,000. And then you would recognize that ln of e, that thing just cancels out and we just get t is equal to ln of 1,000. And we would get an approximation from our calculator there. Ln of 1,000 is about 6.908. And again, takes 2 seconds to sub that back in your original equation and double check that you have the right thing. All right, another example. 15 raised to the 4x is equal to 30. So notice that our examples are starting to get a little more fun, right? A little more interesting because we have something in that exponent besides just x. So we're going to use that same technique. And we're going to think about taking a log with the same base as the exponent on both sides. So the base of this exponent is 15, so let's take log base 15 of both sides of the equation. All right, and so what happens on the left-hand side? That log base 15 of 15, that cancels out, and we're left with 4x on the left-hand side. And then on the right-hand side, if we were going to write this as a ratio of logs, would be log of 30 over log of 15. Okay, so now we want to isolate x. And I think I've said this once or twice before. If I want to get rid of a coefficient here, but I have a fraction already on the other side, I want to think about it less as dividing by 4 and more as multiplying by 1/4. Okay, and so if I multiply both sides of my equation by 1/4, that's going to give us x is equal to 1/4 of log of 30 over log of 15, which we would say is the same as log of 30 over 4 log of 15. And then we would use our calculator to go ahead and get an approximation there. All right, so we get an approximation of 0.314. That's going to give us a value that we can sub back into our original equation and crunch it in our calculator. All right, now let's use that other technique, and we'll see which technique you like better. Some students like one while other students like another. So remember that technique would be taking a natural log of both sides of the equation. So we would have here ln of 15 to the 4x is equal to ln of 30. And then we're going to shift this exponent by using the power rule and treat it like a coefficient to this ln of 15. So we would have 4 times x times ln of 15 is equal to ln of 30. And so now we want to isolate x. And remember that this is 4 times x times ln of 15. So I'm going to divide out everything but the x. I'm going to divide out the 4 and the ln of 15. Okay, and so when I do that, I end up with ln of 30 divided by 4 ln of 15, and that whole thing is equal to x. We can go ahead and get an approximation from our calculator, which should be the exact same thing. All right, final example. We have 1,000 times e to the 4x is equal to 5,000. And the thing that's different here is the exponential piece is not isolated, right? It's encumbered by this 1,000. And so we want to get it out of the grips of this 1,000 by dividing it out on both sides. So we would divide both sides by 1,000. Oh, and isn't that nicer looking, right? E to the 4x is equal to 5. So let's go ahead and get rid of that e by taking an ln, taking a natural log of both sides of the equation. So we've got ln of e to the 4x is equal to ln of 5. And that ln and e on the left-hand side, they cancel each other out. We are left with just 4x is equal to ln of 5. And then when we divide out the 4, we get ln of 5 divided by 4 is equal to x. And we can get an approximation from that as well. And that wraps up this video on solving exponential equations. In the next video, we're going to talk a little bit about applications of exponential functions. How is this relevant? How can this be used in real life? See you then.